to my channel, and today I'm going to be talking about reduction formulas. So what is a reduction formula and why is it important? Well, to truly understand what reduction formula actually means, we must talk about the basics of integration. Now we're going to be talking about a generalization. This is going to be important when essentially explaining the reduction formula in itself. So let's just take an example of an integral that many people would encounter in a standard integral calculus class. So let's just say we have the integral of x cubed dx. This is just equal to x raised to the power of 4 all over 4 plus c. Now, you may be wondering, is there a specific type of formula to do this? Because in mathematics, we have tons of formulas. The main goal of mathematics is to try to quantify, essentially, and extend from the basic axioms in logic, and pretty much go further out. That's essentially what mathematics is trying to achieve. Trying to understand the world through logic. We're not applying it to the world, but rather operating on a set of fundamental axioms and trying to keep building upon it to create this abstract method of reasoning. Now, essentially, as you can see over here, we have a generalization. Well, this is not a generalization, but we have essentially a specification over here. How do we create a generalization? Well, a generalization is essentially covers all possible states and can essentially give a specific term that we plug in to get our results. Moreover, it's just a specific type of formula. Now, the generalization in this case is the integral of x raised to the power of n dx is equal to x to the n plus 1 all over n plus 1 plus c. Now, why is this actually important? Well, the reason is because if we have x raised to the power of 364, then, and we take the integral of that, we just plug in 364 over here, and we get our answer. The plus c is just supposed to be a constant. Now, as you can see over here, this is pretty simple. We generalize it. We're covering all possible states of the term that is specified over here. The term that's specified is, well, the specific part of the term that's specified is the power. So we're covering all possible variant states of that power, which is n. So essentially, we're just covering all possible states, or just creating a formula. We're trying to generalize it, to make it a general formula. That's essentially what a generalization is. Now that we've talked about what a generalization actually is, let's talk about a technique in integration that is very important, especially with the problem we're going to be dealing with. Now, this problem is essentially, we have the integral of 5x dx. How would we solve this? Now notice we're given the formula integral x to the n equals x to the n plus 1 all over n plus 1. Now notice when we just have an x by itself, this is actually equal to x raised to the power of 1. So as you can see, we have defined our n over here. Our n is equal to 1. Now, as you can see over here, we got x to the 1. We have it over here. But as you can see, we have a coefficient to this term. Now, how do we get rid of that coefficient, or what do we do with that coefficient, essentially? Well, to deal with this coefficient, we can just take it out, because it's actually multiplied to the specific term over here. Or more clearly, this is 5 times the integral of x to the 1 dx. This is essentially the same thing. Notice that when we have a common factor that is distributed to all terms of an integral, we can pull that factor outside the integral. As you can see, we just did that. We're given this formula. Then, we can just add plus c over there for the general formula, but as you can see over here, x to the 1, so we're adding 1 to that, so that's going to be x squared over 2 times 5. So we just get, this is equal to x squared over 2, so 5x squared over 2 plus c. This is essentially just going to be our formula. So this is 5/2 x squared plus c. Now this is essentially just going to be our answer over here, and this is a technique that we need to know. Last but not least, we have another technique. I've already made a video about this technique, so please visit it. It's about integration by parts. So we have, essentially, we'll erase this now. So it's about integration by parts. And it's a formula stating that when we have an integral of a product, u dv, this is just equal to uv minus the integral of v du. Now you might be wondering, well, if we have an integral already, aren't we making this more complex, as you can see over here? And secondly, we have, how do we know which is u and which is dv? Does it come in this order? And how do we know something's a dv? Well, notice that dv just represents the differentiated version of v. So when we're taking the derivative of v, we get dv. So that's one thing. And when we're taking the derivative of u, we get essentially du. Now, how do we define this? Well, we have a freedom of choice to essentially pick anything to be u and anything to be dv. So remember that u is one thing and dv is one thing. So essentially we have a freedom of choice to pick anything. But once we pick it, we have to follow the standard process over here. Now you also may be wondering, if we're starting from this and we have another integral and a term beside it, doesn't this make things more complex when looking at it? Yes and no. The thing is, as you can see over here, this integral is supposed to be simpler than the one with this integral, which means that if we don't know how to solve this integral, use this formula, then we can solve this simpler integral, we can simplify the terms, and therefore this is equal to that integral. This is called the integration by parts formula. Okay. Now that we've talked about this formula, we have now started our journey to explain what a reduction formula actually means. So what is a reduction formula? Well, a reduction formula is trying to reduce the complexity of an integral. And most of the times the integral has, for example, something to a very high power. Let's just say we try to find the integral of sine 365 x dx. Now you may be wondering, why is it 365 over here? Notice that this is the same thing as the integral of sine x all raised to the power of 365. This is just a simpler notation. Notice that you'll see this notation on top a lot when we go to calculus and other forms of calculus. Okay, so now that we've got this, how do we essentially try to solve this? Well, this is pretty hard to solve. We need a formula to essentially reduce this. This is called a reduction formula because we're trying to reduce the complexity, and mainly we're trying to reduce the power. Most of these have an arbitrary number which states for our power. So we have an arbitrary power over here, which in this case is 365. We're trying to reduce the power to make it simpler, because in integration we're increasing the power. Now, usually we'd like to deal with things that have a very less power. So let's just say we have 3 squared and 3 to the 365, which is simpler. Obviously this, because we could just do 3 times 3, therefore this is 9. This we had to multiply 3 times 3 times 3 times 3 times 3 times 3 times 3, all the way till we get to the 365th term. Now, this is why we prefer smaller powers. So our reduction formula is essentially supposed to try to reduce the powers in reducing the complexity of an integral. And it's also doing this by trying to generalize it. We're trying to generalize this into an n. So trying to cover all possible states. So if we're trying to find a reduction formula of sine 365 of x, we're essentially just trying to find the reduction formula of sine to the n of x. So what this means is we have this the same, well, this leads to the integral of sine n of x dx. This is the same thing. We're trying to find a reduction formula for the most generalized term, so we can then apply it here. So we can have a generalized reduction formula for pretty much anything. So reduction formulas are pretty much generalized. Try to find a generalized formula. Now, that's essentially what a reduction formula actually means. But how do we actually know what a reduction formula is, and how do we actually calculate it? So here's an example of trying to find a reduction formula. Notice this involves all the techniques which we just talked about previously, and some differentiation. Okay, we're going to try to find a reduction formula of sine n of x than one we just talked about. So what's the first thing we're going to do? Notice that as you can see over here, this is in one part. Right now you can think, oh, how are we going to be using any type of integration by parts on this integral over here? Well, by the basic rules of algebra and logic, this is the same as the integral of sine to the n minus 1 x multiplied by sine of x. Why? Notice that this has just a power of 1. Notice that since they're the same things, we can add the exponents by the laws of algebra, laws of exponents. Then we have n minus 1 plus 1. This just gives us n. Now, as you can see over here, we have to write the dx. As you can see, we have sine to the n minus 1 of x times sine x. Now, we can just apply the integration by parts formula now. Okay, so let's apply the integration by parts formula. Notice we're starting from the generalized form over here. We're starting from the generalized form. So, as you can see, we have the continuum. So we have to pick our u and dv. Notice the main thing of the reduction formula is trying to reduce the power, which then leads to the reduced complexity. Now you may be wondering, then why do we need to pretty much know that piece of information? Don't we just apply the integration by parts formula, get our answer, and then we're done? Actually, there's actually a couple steps between. And in order to use the integration by parts formula effectively, to create a reduction formula, we must know that we're trying to decrease the power. So essentially, we can pick our dv into something that we can integrate because we want to create a dv into a v. Well, that's just going to be sine x. We're going to pick our dv to be sine x. Well, u has to be sine n minus 1 of x. Because differentiation essentially decreases the power, and that's what we want. Okay, now that we've decided that, let's find our du. By using the laws of differentiation, we just have n minus 1 sine n minus 2 of x, and this is multiplied by cosine x. Because essentially the differentiation of sine x is equal to cosine x. Okay, now that we've got that, we have to do v. To do that, we have to integrate this. Notice that in order to find reduction formulas, we previously have to know some integration, like the integration by parts formula and some other standard integrals. Notice that we can essentially find pretty much any integral by using graphical versions of these, but that'll just be too tedious. So we want to get this algebraic type of form. In mathematics, we have a geometrical perspective and an algebraic perspective. Pure mathematicians, which deal with both perspectives, first always start with the geometrical perspective. Isaac Newton, the creator of calculus, loved geometry. Albert Einstein, the creator of general relativity, which is a highly advanced theory that involves partial differential equations, also has a lot of geometry in it, pretty much advanced geometry. Not Euclidean geometry, but advanced geometry. Okay, so now that we've talked about that, people first start from the geometrical perspective and then try to create the algebraic perspective. We're trying to create the algebraic perspective over here. Notice that we already know from our previous knowledge the integral of sine x. This is just going to be minus cosine x. Okay, so now that essentially we've got this, because essentially we have the integral of sine x equals minus cosine x, and minus cosine, okay. So essentially we've got this over here. Now we can start just plugging it in to the essential formula. How do we do this? Well, we have a variety of ways, but we have to follow the formula, which is u v minus the integral of v du. Okay. Okay, so let's do this. So as you can see, we take essentially u, which is sine n minus 1 of x, times v. Notice we'll put the minus sign in front, so cosine of x, minus the integral of v, which is minus cosine of x, du. Now, it's just this. So we have n minus 1 sine to n minus 2 of x times cosine of x dx. Okay, as you can see, we have a pretty long integral over here. Now, we can pretty much just simplify it. So let's just pause this part. Let's pause this part and focus on the integral and how we're trying to simplify it. Notice we've used one of our techniques that we've discussed. Well, technically two. We talked about the generalization technique and we talked about the integration by parts formula. The remaining technique is what we're going to be implementing right now. So as you can see, we have minus the integral. So we're pausing this part of minus cosine of x times n minus 1 times sine n minus 2 x times cosine x dx. Now, you might be wondering about the technique that we talked about. So I said that if we essentially have any common factor distributed among all terms, we can take that out of the integral. Well, what's a common factor? As you can see, we have a minus sign in front of all of these. Therefore, we can factor out a minus 1. If we do, we get minus 1 times minus. Therefore, this is a positive. So this integral is actually going to be plus the integral of cosine x times n minus 1 sine n minus 2 x times cosine of x dx. Okay, now what can we factor out? Well, in order to truly factor out another term or another part of this term over here, we must talk about essentially the generalization part. Now, notice that we're taking the integral with respect to x. So x is our main thing. N is just an arbitrary constant, an arbitrary number. And if I expressed that when I talked about essentially generalization. So if n is just an arbitrary number, it's just a substitute variable for a number, then what happens if we just treat n as an actual number? So can't we factor that out? And indeed, we can. So therefore, we just have n minus 1 integral, and this is also plus. Then we have cosine of x times sine n minus 2 of x cosine of x dx. Now this seems more simple, but we need something else. We need to simplify this even more, and we can just do this with basic algebraic operations. We know that we can multiply two of the same variables together. As you can see, this is two of the same trigonometric functions, therefore we can multiply them. So let's essentially erase this top part over here. Now, if we erase this top part, let's draw a line to this, saying that this is our reference. Okay, this is our reference section. Now let's continue working. So we'll just say work. So let's essentially take the bottom integral. Notice we put this part on pause still. Then we have the integral of cosine squared x times sine of n minus 2 x dx. Notice that since cosine of x and cosine of x are trigonometric functions and the same trigonometric functions, we can essentially combine them. If x times x is x squared, cosine of x times cosine of x is cosine of x squared. And we can write it like this. Now, as you can see, we seem to have no hope. We can't simplify, we can't do anything. Well, what can we do? Now, you may be thinking, what about integration by parts? Because we have a product. And that seems like a good idea at first, but that's not a good idea. The important thing in a reduction formula is we're trying to reformulate an integral that essentially is the same or partly the same as the original integral or has a lower power, but other than that is mostly the same with the original integral. What is the original integral? we'll type OG. This is the integral of essentially sine raised to the n of x dx. Okay, now that we have essentially talked about that, let's continue doing this. So we're trying to reformulate this integral from this integral. What can we do? Now I made a 3-part series on trigonometric identities. Trigonometric identities are essentially identities that when we combine different trigonometric functions, we get a trigonometric function that's the result, but it actually seems pretty surprising. Or in other words, cosine squared x plus sine squared x is equal to 1. And this seems pretty surprising. We're combining two trigonometric functions to outcome a trigonometric function or something else. As you can see, we got 1. Now this is actually pretty surprising because we got cosine squared of x plus sine squared of x is equal to 1. You'll see this a lot in calculus, and I already talked about this trigonometric identity and tons of other trigonometric identities on my video on trigonometric identities. So I have a 3-part series on that. Okay. Now let's continue with this. So we have this over here, and the identity that I just talked about, cosine squared x plus sine squared x is equal to 1, we can manipulate algebraically to just say that 1 minus sine squared x is equal to cosine squared x. We're going to substitute this for cosine squared x. We get plus n minus 1 integral of 1 minus sine squared x sine of n minus 2 x dx. Okay, if we do this, we can distribute now. So as you can see, over here we'll get plus n minus 1, the integral of sine n minus 2 of x, and then minus, so we can, since we're multiplying these, we can add the exponents, then we just get sine n of x dx. Okay, as you can see over here, well, we kind of have variant of the original integral. But is this sufficient enough? Well, partially. There's another thing that we have to realize. So, essentially, let's erase this part over here. Keep this over there. And we'll talk about this in this part. Okay. So, continuing, as you can see over here, we have this integral over here. Now, notice that let's just say we have the integral of x cubed plus x to the 4 dx. Now you might be wondering, do we have a generalized integral for this? Well, actually, we pretty much don't have a generalized integral. We can make one, but the thing is, the integral of x cubed plus x raised to the power 4 is just the same as the integral of x cubed plus the integral of x to the power 4. And this is literally the same thing. So, we can use this property to essentially just distribute this over here. So as you can see over here, we can just distribute the integral sign. So what can we do? Well, if we erase this part, you can go on top and say plus n minus 1 times the integral of sine n minus 2 of x. Then minus n minus 1 the integral of sine n of x. Okay, as you can see over here, we have two different integrals. And why do we have the n minus 1 over here? Well, as you can see, we distribute this. So when we essentially just take this off, since this is supposed to be a common factor of these, we have to distribute it across the integral signs, and hence that's the reason they're over there. And so now that we have this cleaner integral, we can take this pause button off to this part and start adding it in. So as you can see, we're going to have essentially minus sine n minus 1 x times cosine x. And now we can start implementing this plus n minus 1 integral sine n minus 2x dx. We can add the dx's. And then minus n minus 1 integral sine nx dx. Okay. Now let's just clean the bottom part and continue writing over here. Okay. So as you can see over here, we have this big integral over here. Now, let's erase the bottom parts because we don't need them anymore. And let's now start observing this integral over here. This is the most important crucial part. We have to start including an equal sign. Now you may be wondering, what is this equal to? Well, this is all equal to the generalized integral. So what is the generalized integral? Well, that's the integral of sine n x dx. And this is equal to, essentially, minus sine n minus 1 x cosine x. Well, let's just shift this over here so that we have the integral sine n x dx is equal to minus sine n minus 1 x cosine x plus n minus 1 integral sine n minus 2 x minus n minus 1 integral sine n x dx. Okay, now that we have this big integral formula over here, we can now add this integral to the other side. Now, I talked about this a little bit earlier. I said that when we're trying to arrive at a similar type of integral, a variant, or the exact same type of integral, we have the exact same type of integral over here. Now, this is the most important step of all that I would say. The reason, well, without doing this step, we wouldn't really have a reduction formula. So, we're adding this. There's supposed to be a dx over here. And sine x dx. Adding this to both sides. We can essentially factor out the integrals. So we have n minus 1 plus 1 times the integral of sine n x dx, and we'll call all of this, let's just call k for now because we don't want to rewrite it all the time. So now we've got this specific type of format, and you may be wondering, how did we get this type of format? Well, the reason and how we got this type of format is pretty simple. So let's just say we have 5x plus 5. And we want to do the backwards of the distributive property. Well, we get factor out of 5, therefore get x plus 1. This is the same thing because we can distribute the 5 and get the same thing. Similarly, over here, we have the n minus 1 over here. Now, as you can see, when we combine both integrals, we have the integral of sine n x dx plus n minus 1 times the integral of sine n x dx. And as you can see, these are the same things. We can factor them out to get n minus 1 plus 1 times the integral of sine n x dx. This is how we got over there. Okay. Now, let's continue. As you can see over here, we can simplify this part to just get n, because n minus 1 plus 1 is just n. So we got n times the integral of sine n x plus, well, dx is equal to k. Now, what can we do? We can divide by n, and we get the integral of sine mx dx equal to k over n. And this is going to be our reduction formula. Let's just write this down to essentially just have a fuller, neat form of the reduction formula. So, as you can see over here, the reduction formula is integral of sine mx dx is equal to minus sine and minus 1 x cosine x plus n minus 1 integral. So we can take this off now. Sine n minus 2 x dx all over n. And this is going to be our reduction formula. Okay. So, let's recap. So what we did at the beginning of the video, we talked about the three main techniques to essentially better our understanding of what a reduction formula actually means. So we talked about a generalization. We're trying to cover all possible states. Then we talked about the technique where we can factor out the common factor outside the integral. And then we talked about the integration by parts formula. Originally, we started by the integral of sine of x raised to the power of n dx, but we split it into the sine to the n minus 1x times sine x. Now, the reason for doing this is because it makes this simpler, and we can use the integration by parts formula to actually solve this. Now, notice that when we're doing reduction formulas, unlike pretty much any other formulas that you've previously seen, we have a pretty long formula over here. And, as you can see, the reduction formula's processes and steps are quite confusing and very hard to grasp. You have to take a lot of practice to try to understand what this formula actually does and understand the process they go through, because there isn't a lot of information online. Okay, now that we've talked about this, let's write it into a neater form on top, and we can make this video to an end. So, our reduction formula is essentially a formula that encapsulates all possible states of a specific type of integral that we're trying to make simpler. Example of this is the reduction formula for sine x raised to the power of n. We can also do the same for cosine, but we're not doing it in this video. So the integral of sine nx dx is equal to minus sine n minus 1 x cosine x plus n minus 1 integral sine n minus 2 x dx all over n. And this is going to be a reduction formula. Okay. Now that we've talked about this, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.